All right, so I'm doing number 2 here. Number 2. And I'm told, now folks, remember, it's great that you're working together. Just try to keep it down to a low din so that people can hear me if they want to. All right, but 2, yes, work together. If you don't need number 2, get up another one that you're working on and work on it. And if you need help from someone, get them to help you. So I'm going to, yeah, we can turn the light. Sure. Does that work better for you? Okay, that works for everyone. That's great for me. But T is running at this speed in this direction, so that's its velocity there. So mine is 18.9 meters a second at 36 degrees north of west. So I'm looking. Here's my vector diagram. 36 degrees north of west. So I'm going to take north as up my paper, and west, therefore, is to the left. So if I draw this, it's going to be that direction, where this angle, I want to make sure I get my numbers right here, 36. This angle is 36 degrees. I got to make this background a little lighter. And the length of this is 18.9 meters per second. Right? There's the information they've given me. And they've said find the north and the west components. Then do yours. It'll be the same method, but you're right, you have got to do your own math. And so I'm going to draw my 2 components of my vector, my westerly component and my northerly component. So this is my y. This is my vector diagram. Yes? Does that make sense? Katie? Okay. So that's what I'm looking for vector diagram wise. All right, now I have to remember. I'm gonna just do myself a little sketch down here just to help me out, so I can label it up. 18.9 meters per second, 36 degrees, and I have a right triangle here. So I'm thinking, okay, I want to know. I'm going to call this W and this N for west and north. Okay? So I can label them anything I'd like. And I'm in a right triangle, and I want to know the legs. I start thinking SOHCAHTOA. You know, SOHCAHTOA. And I want to know N, which is opposite my angle. And so the one that involves opposite and the angle of the hypotenuse is So I have sine of 36 degrees equals opposite, which is N, over hypotenuse, 18.9 meters per second. Rearrange that, 18.9 meters per second, sine 36 degrees equals 10. Am I going too fast for anybody? Okay. I'll take a drink of my coffee then. I'm going to jump up. You got it, ma'am. Well, I gotta get the calculator app up here. 18.9 sine 36. What's the most common mistake at this point? Your calculator's in something else besides degrees, right? Make sure your calculator's in degrees, especially if you had math right before this, and then made you change it to radians. So I have some scientific calculators, but I would suggest applying your own. You know, I do have some of the more simple, more basic ones, so you need to borrow one. Yeah, right up here, this is the cabinet with the sunset on it. There's a white container of them. The way you change it to degrees, you hit the mode. You hit the mode button, and you look for which one is highlighted. And if radians is highlighted, arrow down to the word degrees and hit enter. And then you can do quit out of that, which is second mode. I'm going to renew my request to get the TI app here, so I can show you right on the board. I think they just forgot. So I did this, and I got 11, for my numbers, 11.1 meters per second equals n. So I'm going to try that, see if that works. 11.1. Submit answer. Cross my fingers. Yay! I love that little green check. You ready to do W? Okay, to do W, I noticed that W is adjacent to my angle, so I'm going to use ka, which tells me that cosine of 36 degrees equals adjacent W over the hypotenuse of 18.9 meters per second. So I have 18.9 meters per second cosine 36 degrees equals W. And I get 15.3 meters per second. And now I just got to check and see if I'm right. Yeah, yes, sir. I just did the W. Because it's adjacent to the angle, right, it's next to it, I'm using cosine, the ka from SOHCAHTOA. So I'm doing basically the same idea, except W is adjacent, so its cosine of the angle is adjacent over hypotenuse, and then I solve for W. So it's just that different ratio because of where the angle is compared to the size. Let me check and make sure I got it right. 15.3. And I did. Yep. Yeah, I just wanted to check that I didn't put down the wrong answer. All right, let's do number 6. Oh, you got a 45-degree angle? They were nice to you then. What do we know about the legs of a 45, 45, 90 triangle? They're the same. Are we talking about number 2? Yeah, you're asked for the 2 legs. But as soon as you find one, you find the other. You're in number 6. Number 6, yeah. And in number 6, I'm given 2 vectors. I'm given vector v1 and vector v2. And I'm asked to find v1 plus v2, right? What are the components and length of a vector with the sum of these 2 vectors? We did this, what they call component notation here, is just a different nomenclature for unit vector notation. So I'm going to write these again, but I'm going to write them as unit vectors so they fit with what we talked about the other day. So I'm going to write v1, which would be positive 4.0 I plus 1.2 J, huh? I either place you could write it, because I'm just kind of trying to, in my brain, get it into a form that we talked about. Minus 15.0 K. And then V2 is positive 3.3 I minus 3.2 J. Remember, you're going to have different values here. Minus 1.6 K. So I'm getting them into that form. We didn't use that parentheses form. So I'm trying to translate into information you understand. Because we did do unit vectors. Okay. So now this one is kind of fun. These are kind of funky to draw. So I'm going to do V1 in blue. I tell you, the drawing of this will be the hardest. So I'm going to go 4 in the I direction, 1.2 up. Let's see. And then negative 15, so I'm going to go into the board 15. Oh, okay, quite frankly, if I asked you to draw this one, I would take almost anything. I'm going to try to draw it the best I can for you, but I would basically take anything. I'm going to do a perspective drawing here, that here's a plane, I is in this direction, J is in this direction, and K is in that direction. Just bear with me. I'm going to show you how to do it, but basically whatever you would draw here on this one would be fine with me. No, your directions would be the same. Well, the I, J, and K, yes. So I'm going to try to draw this one. I'm going to go 4 in the I direction, 1.2 in the J direction, and then down 15. So my vector, this one, would be a vector in that direction. Yeah, it does. That's why I'm saying whatever you draw here, because I'm trying to draw three-dimensionally. Yeah, just so I can, when I'm flipping through it, I grade something. The way you would know how to draw this is that you got to think three-dimensional, and that's why we're going over it, right? All right. Hey, here's my diagram. While you were at lunch, I did my beautiful diagram here. Yay, isn't it pretty? And now I want to add these two together. And this is one thing I like about having these in unit vector notation. Here is V1 plus V2. 7.3i minus 2.0j. I just add the components. Minus 16.6k. That's the components of my answer. So that's what I'm going to type in on here. Whatever I had there, yep. 7.3.
You just put in 7.3, don't put in the
Right, because the I is that first one, 7.3, and then what do I have? Negative 2 and negative. Where did I get those numbers from? No, let me just.
It's always IJK.
IJK, yep.
And so you just take them in order as they come up on the thing? Like
Yep.
That's how it comes in.
Yeah, because remember I is in the.
So why do you need to draw a picture for that? Like, why does that require a
Just
picture?
because we're getting in the habit of drawing pictures.
Right,
And I think more people would be screwed up if I said, well, do pictures for everyone except that one.
Yeah, wait, hold on. Can you back up the one we just said? Why do you have nothing done?
Because I haven't done that yet.
But it still says you got it right.
Yes, I did. I got to write the parts that I put in.
And then do you just add those together?
Yeah. So, yeah, exactly. So now it asks you for the length of this vector. Well, in 2 dimensions we have Pythagoras, right? A squared plus b squared is c squared. Well, if we translate Pythagoras into 3 dimensions, and I can show you why this is true. We have what I call 3D Pythagoras, which is a squared plus b squared plus c squared equals d squared. So the length of the x component squared plus the length of the y component squared plus the length of the z component squared equals the magnitude of the whole thing. Yes. Yep. The answer that I found in the red, the 7.3 is my x component because it's next to I. My 2.0 is my y component because it's next to j. And the 16.6 is my z component because it's in the k direction. Remember, I, j, k, x, y, z. It's that alphabetical thing. There to help us. So, do what? Yeah. 4 plus 3.3 is 7.3 because I'm adding the vectors. So I add up the components of the vectors. Yeah. Yeah, so 7.3 squared plus 2.0 squared. Of course, it's the length of those components. Does direction matter? No. I mean, it matters what dimension they're in, but not if they're positive or negative. Equals d squared. Yes. Sure. You know where the sign up book is, right? D is, let's see, 7.3 squared plus 4 plus 16.6 squared. Square root that. I get 18.2. Why not? Did you forget to square root the d? Because it's a squared plus b squared plus c squared equals d squared. I'm solving just for d. Yeah. She's like tired. No, I added the squares of them up. I did square them. Then you're going to get, well, if they're any different, you're going to get a different answer. If they're smaller, then you're going to get a smaller answer. Yeah, I'm just making sure I didn't screw up. There you go. I didn't screw up. All right. We're doing number 7 here. And 7 asks us, if we've got a plane moving in this direction at this velocity, find first the components of it, and then if it travels for a certain length of time, how far the components of its displacement. So I'm assuming that you guys could do part A here, finding the components. Given that you have theta in there, right? You could find the opposite side and the adjacent side like we did in, what was it, number 2 that we did today? Yes? Oh. So I'm going to move and start doing part B of this. That would be my vector diagram. Here's part B. So, and in part B, I'm asked the components of the displacement of the aircraft. There's a small little factoid that you need here. Velocity and displacement are always in the same direction. So the velocity and the displacement here have to be at the exact same direction. So if this is the direction of my velocity, the direction of this green arrow, my displacement's also going to be in that exact direction. So I'm going to draw my displacement like this. That's my D. And then I'm going to do, I want its northerly and westerly components, and I know this angle is 41.5 degrees. And now the question, and this is something you'll get better at with time as you do more and more of these. The adjacent side is related to what trig function? The adjacent one. Cosine. So this side is D cosine 41.5 degrees. And the opposite side is going to be D sine 41.5 degrees. I got those from like sine of 41.5 degrees equals opposite, call it west, over hypotenuse, which is D, and just rearranged it like we did in question 1 or question 2, first one we did today. But now the question, how do I know D? D, I got to go back to what I remember from what the linear motion, because I know that D equals D naught plus V initial T plus 1/2 AT squared. Told me though I'm not accelerating, so that whole term is 0. I'll call where I started 0, and I'm left with D equals VT, right? So I want to find D. I'm told I travel for 3 hours at 775 kilometers an hour, so my D is going to be 775 kilometers an hour, and I do that for 3.00 hours. And I'm going to figure out what my D is, and then I can put it into the... I read it in the problem. It tells me in part B that I travel for 3 hours. Right, because 3 hours is my time. They give me my velocity. Think about it. Sometimes it's easier to think about it in simpler numbers. If you're moving 10 miles an hour and you travel for 3 hours, how far did you go? 30 miles. Same concept here, right? I'm moving 775 kilometers every hour for 3 hours, so. Right, so now I know my hypotenuse here, and I can find my 2 legs, like I did in number 2 and in the first part of this one. Yeah. Right, and notice I wrote those right on the legs here.